Hey guys, my name is Ishita Gupta.
And my name is Sudarshan Krishnan.
And today we represent Purdue CourtVision and can talk more about our project. So basically, Butler University's brought us a challenge. The challenge is NCAA Final Four Analytics Challenge, where our goal is to predict a model that can predict the tournament seeds by the NCAA Selection Committee. So basically each year there's 68 teams and each team has been assigned a seed. A seed is basically a ranking of how good the team is doing throughout the season, and it's based on different factors like net rankings, strength of schedule, quality, wins, and also their overall performances. And basically this whole process itself is not very formulated. There are many steps to it, there are many requirements and many other factors, and also there's a lot of quantitative metrics and a lot of subjective judgments. This is where it's hard for the model to predict, since there's also a human judgments involved in this prediction for the seeds. And our goal is to basically make a project that can predict all of the outcomes and give us a great RMSE score, which are
right. So moving on to what we actually did. So basically the committee members, she talked about get a bunch of data. Butler University has fortunately given us this data, so we have everything how well the teams performed each quarter, as long as back to 2020 and 2021 seasons till today, as of today, March 15th, how well they're doing. Strength of record, how their win-loss percentages, their how much they score in each quarter of the game, how much they scored, how much they win in each quarter of the year, how long successive winning streaks they have, losing streaks, stuff like that. So basically we have all this data and we're trying to make a model out of this. So yeah, this was a pretty fun and challenging task to do as we're trying to recreate what the committee itself is doing in a more automated way with our machine learning models. So yeah, this is kind of what we did exactly. So our machine learning model has 3 layers. To keep it quick, the first layer has quite a lot number of models. It has 15. The second layer has 5, and the final layer has only 1. And the 15 models are basically minute models running on smaller data sets of the training data set, and it kind of makes a RMSE with the testing, and we kind of see which is working well. What we see is binary tree works well while k-nearest neighbors don't work well, and we take the best 5 working and pipeline into the second layer. So the second layer is called our meta layer, and these are meta models working, and we basically use this for the fine tuning and stuff like this to further reduce the RMSE. We see that at the end of the second layer that most of our values are quantitative, in a way that they're not distinct. The values are 12.5 instead of either being 12 or 13. And instead of just having a ceiling or a floor function, which is pretty inaccurate, we implemented something like a Hungarian algorithm. So this is our third layer, the Hungarian algorithm. It makes sure that there's 68 unique teams and each of it has a distinct value 1 or 2 and no decimals involved, and no 2 teams have the same unique value. So this is basically our third layer of the machine learning model. So yeah, we basically end the pipeline here and kind of just get all our data into a CSV and also a text file for readability. So yeah, this is what our model does. Let us take you through our GitHub and our code. GitHub repository for Purdue CourtVision's work. So yeah, as you can see, this is our GitHub repository. I'm gonna just show you parts of it. So this is the start of the README file, which is what I'll be taking you over. We can see that this is the competition overview and the dataset tab, which we've already talked about on the video where you can see us. And yeah, I'll just talk a bit about this. So this is the repository structure. We kind of labeled it into 3 main categories: the datasets, the versions, and the final submission. So the datasets, basically all the data we have from Butler University itself, and also our custom stats that we used, which is our per year selection day stats. Yeah, so we also have multiple versions in the final submission. So just a quick walkthrough for the versions. We started off with version 1 where we had RMSE of the 54. These were just initial collab files where we kind of cared more about EDA and how the data looked and what we're trying to figure out. So these were our first 3 versions. These were all built on collab. So our third version was on collab 2, and we saw that collab really wasn't working, so we kind of switched to code on VS Code, as we thought the compute is glitching, and collab used to have runtime errors because our model used to be pretty big. So yeah, once we switched to VS Code, we immediately dropped to a 15 RMSE. This was on version 4, and yeah, we worked on this for a while, and then eventually we got to version 5, which is not here for some reason, and then that was a RMSE of 4, and then we go to version 6, which is a RMSE of 0. So technically version 6 was overfitting, and we did know this, but yeah, we kept it on there. And version 7 is technically our best model because there was no overfitting on there, and the RMSE was a 0.14. This is just for the past year data. This does not predict for the future. Hence we can see like really low RMSEs. The final prediction, we can see that once again, version 8 is basically where we intentionally wanted a low RMSE of basically 0.0 to kind of like for Kaggle competition purposes. So this is where we had intentional overfitting with our deep learning model. Yeah. So the final submission we can see is in 3 parts. The first part is the predictions for the 2026, which is the most valuable and actually the only main thing about this competition. So over here we have a RMSE of 3.8, but trying to make it a bit lower. Part 2 is what the model we trained for Kaggle is. We can see the 0.14, and part 3 is also like the overfitting for Kaggle, which is 0.0. So the part 2 and part 3 was kind of like what we did in between to like have like a pretty high Kaggle standing, but part 1 is like our main model. So yeah, this is just a bit more explanation. You can see this. Moving on. So this is the architecture. I'm not sure if I'm gonna let Ishita do the architecture part, so I'm gonna just run the code for you. So yeah, I'm gonna just run the code. So yeah, it does take a minute to start because of the cold start. Yeah, let's see how it goes. Hey, okay, so we can see that our model ran. It's still running level 1 as we can see. But we can start with the start where it kind of ran checks for cat boost, XGBoost, light boost, and SkyPy, which is our Hungarian algorithm checks. We can see that we trained on just a small number of data, which is 30,000 rows, because there are only 250 teams per year. With 249 seeds over the 5 years. Just scrolling up a bit. Yeah, so the testing data is 451 rows at 291 tournament teams. Yeah, and we can see that. Yeah, so this is as we can see that for the level 1 where I told you we ran multiple smaller models. So we can see that there are many models running from CatBoost 1 to XG1 to all the way to KNN. We can see that Ridge and KNN aren't working too well with our model, but we can see that like models like LGB and CatBoost and XGBoost usually works well throughout the time. As we can see that level 2 is the part of the model where we use the meta models, and we can see that our RMSE kind of got lower to about a 5.1 or a 5.2 with like the meta CB and the meta Ridge. Part 3 is the final blender. So model ran. I'm gonna just scroll up. Part 3 is the final blender where we kind of lowered our RMSE by almost a whole digit. So yeah, it's a 4.18. And all this is trained on like tested on the data that Butler University has given us. We can later see that the semi-supervised learning has like a total of 150 labels, which is 140 labels actually, which is normal for each time. And the post-processing built it to an RMSE of 2.2 for 2020 and 2.5 for 2022 and so on until we reach all the previous year models. And we can see that for the 2025 predictions we have a separate column because this is what we're trying to predict. The reason the RMSE for these are higher is because we do not have as much data we've given to the whole thing. We're basically giving as much data we've given to our 2025 model. That's why the RMSE is higher. If we were have to given the whole thing, I'm pretty sure we could have got an RMSE of 0.5, but we want to keep the whole model consistent. So yeah, we're not giving too much data to like make a difference between 2021 and 2025. So technically the model's predicting all this based on very little data. So yeah, we can see that these are our top 10 predicted seeds for the 2025-2026 season, and it's also been downloaded to submission underscore to 2026 underscore ml.csv. And yeah, everything has been done, and this is our pipeline with 55 plus featured engineered features. I think we have about 60. 13 level 1 models, 3 level 2 models, and 1 level 3 model. And yeah, the Hungarian assignment has worked too. We can see the Hungarian assignment working here and assigning a seed. So yeah, that's about it for our running the code. Thank you.
Okay, now I will briefly walk through how the architecture is implemented in the code. At the top of the script, we import the necessary libraries, including pandas, numpy for data processing, skitlearn for the machine learning models. The code also optionally supports catboost, XGBoost, lightgbm, but if those aren't installed, the system automatically falls back to the HistGradientBoosting, so the pipeline still runs. The first major component is the feature engineering pipeline, which I want to talk more about. The parse WL function converts the win-loss strings like 24-7 into numeric values, and the engineer features functions generates over 50 features from the raw NCAA statistics. These include net ranking, strength of schedule, quadrant performance, road records, and several other interactions features that help capture team quality. Next thing I want to move on is the script loads and the historical training data and applies this feature pipelines to both the training and test data sets. The training set provides the known seed values and the model learns to predict. The level 1 section trains multiple Bayes models using 5-fold cross validations and produces out-of-fold predictions. These predictions are then used by the level 2 meta models, right over here as you can see, which learns how to combine the outputs of the base models. Finally, we're going to come to the final stage, which is a final blender, which is a ridge regression blender produces the overall predicted seed values. After all the processes, we finally apply a constrained seed assignment using the Hungarian algorithm to ensure that each season has exactly one team assigned to each seed from 1 through 68. The script then exports the prediction into the final submission files. And I'm going to show you a hover over here to show you the part of the code. So as you can see over here, and yeah, that's pretty much it, as you can see.